see, it's on record. So we said that the exam was on the 18th. So this is when it is, and I will send out an email with that. And you were supposed to today pick up the exams from Adil and bring them back Wednesday if you want to make up some extra points that you lost. Today we'll wrap up the capacitance calculation. So we did the resistance and inductance calculations in the past 2 lectures. Today we'll do capacitance calculations. And the way we'll do capacitance calculations is starting from the electric field calculations around the conductor. So here's Adil. So with the exams, that you can take them back. So the process is as follows for the capacitance calculation. We know that the relationship between current and voltage, IC equals C, current and voltage across and through a capacitor. So voltage across a capacitor and current through a capacitor, they're related by this first order differential equation. So for us to calculate capacitance, which is what we need, I will bring dt to one side. So I end up having IC dt is equal to C dVc. If I integrate, right? I end up with the integration of current, which is charge, right? So the integration of current is charge, and the summation of the voltage across the capacitor will result in the final voltage across the capacitor, which is V, right? So this would be the end, summing all the voltage, increases across the capacitor will end up with the final voltage across the capacitor, and this is C and this is Q. So if you have C is equal to Q over V, if you're able to calculate the voltage between the 2 plates, so the voltage between the 2 plates of the capacitor, and you know the charge that is deposited on the plates based on the current that you're pushing through the capacitor to charge it, then you should be able to calculate capacitance. So our objective is to, since we know current, if you have a single phase, power distribution system with current coming this way to feed the load, the same current coming back, I here and I here, we can calculate charge based on current. Current is the time rate of change of charge is the current is the time rate of flow current is the rate of change of charge, right? So we can calculate current from charge or charge from current given one or the other, right? And we will typically know the load current, so you can calculate the corresponding charge. So if you know charge, the thing that's remaining is now between your 2 plates of the capacitor, you have a voltage. This is V between these 2 plates. So you need to be able to calculate the voltage between these 2 points or 2 plates in order to calculate the corresponding capacitance. Transmission line is the same, right? You have a transmission line cable here with a certain voltage and a certain current flowing through it. So you know the current flowing through it, and this current will correspond to a certain charge distributed on the surface of the conductor, and there is a grounded tower, for example, that is of interest, right? That exists. So you would like to calculate the voltage between the conductor and a grounded neutral point, or a grounded potential in the vicinity of the conductor. Because I will show you later that if you have a 3-phase conductor, if you have 3-phase conductors put in this arrangement, if you look at the voltage here, this will be the ground potential as well. This will be this point here will be a ground potential, because again, the electric field from this conductor, electric field from this conductor, electric field from this conductor are going to add up vectorially, and they will sum up to 0 at this location. So it's like calculating the potential difference or the voltage difference between this conductor and ground, right? Between the conductor and some neutral point, some point with a potential of 0, basically. So if you're able to do that, then you can calculate the capacitance between the conductor and ground, or the capacitance between conductors and themselves. If we're able to find the voltage between this conductor and this conductor, the V12 is the voltage between these 2 conductors. if I find the voltage between these two conductors, then I can find the capacitance between them. This capacitance is this is phase A and this is phase B. This is going to be capacitance CAB, right? This is the capacitance between the two phases or the line-to-line capacitance. What do you typically need to build or to solve three-phase power systems, three-phase balanced power systems? You need the single-phase equivalent circuit, right? So I would need the single-phase equivalent capacitance. So if I know my voltage between two lines, I know that there's a relationship between line voltage and phase voltage, and if I know the relationship between line voltage and phase voltage, I can be able to calculate the capacitance in that case as well. So if I calculate the line voltage, I can calculate the phase voltage, and from there I can calculate capacitance, for example. Okay. So the objective is to calculate capacitance because we need that for our transmission line model. Remember, our transmission line model looked something like this. We took this capacitance that we were calculating and divided up JB over 2 here, JB over 2 here. We put half the capacitance on one side of the line, half the capacitance on the other side of the line. So that's the whole objective. We calculated this, we want to figure out how to calculate this. We used it in the last chapter, in the power flow chapter, but now we want to figure out how to calculate it. So we start from electric field, calculate the voltage difference due to that electric field. So that electric field will have a certain strength, and any 2 points that are in an electric field will have a voltage difference between them. If you know this voltage difference and somehow, again, we will do the same thing that we did before. We will have a conductor with electric field emanating from the conductor due to the charge deposited on the conductor. We will find the electric field at 2 different points in space. Then I can take these 2 different points in space, put one on my conductor, put one on the other conductor, or put one on my conductor, put one at the neutral point, put one on my conductor, and then this is due to one conductor. And we will do the same thing for multiple conductors. Again, if one conductor creates an electric field around it, another conductor will also create an electric field around it. If I look at the effect of all of these conductors on the voltage difference between 2 points, how can I deal with it? I will use that same equation that I'm going to come up with for voltage difference between 2 points due to one conductor, right? Then look at the voltage difference between the same 2 points but due to another conductor. Then for a third conductor, the voltage difference between 2 points due to the electric field emanating from that conductor, also at the same 2 points. So I will have many conductors that are. So I have one conductor here that has electric field emanating from it due to the charge deposited on top of it. This electric field, if I look at, remember, electric field will be radial. So the electric field, if I calculate the electric field anywhere around this circle here, or this cylindrical surface, since this is a long conductor, so at a certain radius, the electric field will always be the same. Right? And Gauss's law says what? Closed loop integral of the electric field density is equal to the charge enclosed. Right? So the closed loop integral, it's on the next page, it's on the next slide. So the Gauss's law says the closed loop integral of the electric field density is equal to the charge enclosed. This is the surface at which I will calculate the electric field. The electric field at any point around this surface is the same because I have charge evenly distributed. It's like the assumption for current evenly distributed before, constant current density that we had before. Here I will use a constant charge distribution across the surface. So all of this, any charge here will cause an electric field, and they're all going to be the same. So the strength of the electric field at any radius around the conductor will be the same. So how about if I go to another radius? The electric field strength is in volts per meters, right? It will change at another radius. So the electric field strength will decrease the further away you go. It makes sense, right? It's like the magnetic field. The closer you are to the conductor, there's a strong magnetic field around you. The further you go away, there is less strength of the magnetic field, but it exists. Electric field is the same. You have a conductor with charge. it will cause an electric field around the conductor emanating radially. This electric field will decrease with strength as you go away from the conductor, right? So at 2 radii around the conductor, the electric field strength will be different, right? So if the electric field strength is different, that means there's a voltage difference between a point in space here and a point in space here, right? Due to this conductor. How about this conductor? How about this conductor? This will also have the same effect, right? There will be an electric field emanating radially, electric field emanating radially, and at this point, this conductor affects this point in a certain way, right? This conductor will affect this point as well, and this conductor will also affect this point, right? So this conductor is also affecting the voltage difference between these 2 points of interest. So my 2 points of interest, for example, are here. These are the 2 points I want to calculate V between them, right? The voltage between these 2 points is affected by this conductor's electric field, and this conductor's electric field, and this conductor's electric field as well, right? Right. So all of these conductors, all the 3 conductors, affect the electric field at this point and at this point. So I have to figure out what is the total effect of all the conductors on the electric field between these 2 points, and then that will affect my voltage difference between the 2 points, right? So yeah.
When you talk about shunt capacitance for transmission line,
yeah,
it's there's a capacitance between the line and the 2 other lines, and also the ground.
Yeah, anything that has potential difference will have a capacitance between them.
So it's like the sum of 3 different capacitors.
I'm not sure what you mean.
There's 2 line-to-line capacitors and line-to-ground capacitor. That's what I'm asking.
Yeah, but our equivalent circuit for the transmission line only considers
this one, yeah.
This one.
But it's composed of 3 different sources, these capacitors.
No. So I only want to calculate the capacitance between the line and the ground. There may be capacitances between the line to line, and then there may be inductances between the line to line, like the mutual inductance. But sometimes, when I'm drawing 3-phase circuits, sometimes we didn't talk about considering mutual inductance in the calculation. But if I draw a 3-phase system like this, this has an inductance, this has an inductance, this has an inductance. And this is the inductance of the transmission line, inductance of the transmission line, inductance of the transmission line. And we will go through this in this chapter again, in the context of, in next chapter, sorry. Here I'm drawing the inductors of the transmission lines, right? I am ignoring the mutual coupling. I can include it, right? If you want to complicate things further, you can include the mutual coupling between, it will be very small, right? So since it will be very small, we will typically ignore it, yeah. Certain maybe line models, for example, we are only working with the short line model of the transmission line. Okay, there are other line models that are used for transient analysis. There are other line models that are used for longer transmission lines, right? So in these cases, so for example, for a very long model, there's the transmission line effect, or there's like the reflected wave effect, something called the reflected wave effect occurs. So there, if you actually provide, if you have lightning, for example, striking a certain point on the line, the transmission line model may amplify the lightning waveform by the time it gets to the next tower, for example, right? It's because of the transmission line's capacitances and inductances. It's like it acts like a gain circuit on the transmission. So, but that depends on the model that you use, right? The model that we use is only the short line model. We will not consider. I mean, we will not study the other line models, honestly. So yes, there will be capacitance between line to line. We will not consider those. We will not consider those in the model. Other models, I mean, there are I think the book talks about the medium line model and the long line model as well. I will skip those. Okay? And because they will be used for studying certain phenomena. Like if you take a graduate course in power systems, you will take, for example, there's one typical course that is typically offered in a graduate power systems course would be power system transients. The whole course is only about transients. The whole course is only about power system transients. And there you would have to consider, of course, the different line models and all the capacitances and inductances that you calculate around the system, because they would affect the transient response of the system, right? So here we are, this course is mainly concerned about the steady state performance of the power system, right? So in the steady state performance of the power system, we will only consider the short time model because that's what gives you the power rating of equipment, right? That will not consider some of the transients that are in the system. It's a good question, very good question. Okay, so they exist, but we will not calculate them and we don't care about them for this course. Okay, so we talked about the process, so now let's see what, go through the calculations. So again, from Gauss's law says that the electric field density around the conductor is around the closed surface around the conductor is equal to the charge enclosed. Electric field density can also be written in terms of electric field intensity and the electrical permittivity. If this conductor in space, we will use, so epsilon is like the permeability in the magnetic field, right? It's mu naught mu r, the magnetic field. If the conductor is in air, we will only use mu naught, right? Because mu r is equal to 1 in air, right? Epsilon naught, same thing. Epsilon naught here, if it's, we will only, yes, you're laughing?
No, just because mu is for magnetic.
Yeah. Yeah, I know. I said it's like. I said it was like the magnetic. It's like the magnetic field case when we were talking about mu, the permeability. Here we're talking about epsilon. Yeah, I said this is for the electric field. Right? I was talking about electric field. Yeah. Yeah, this is permittivity. Yeah, permeability and permittivity, right? So. But there, again, there's the permittivity constant is like the permeability constant. It's composed of the effect of air, or the mu naught, and here epsilon naught. Over there was a mu r, and here was here epsilon r as well, right? Epsilon r and mu r are both 1 in air, right? So anyway, so the electric field density around the closed surface is equal to the charge enclosed. This can be written as the permittivity times the electric field strength around the on a closed surface is equal to the charge enclosed. As we were saying, the assumption is that charge is distributed evenly across this conductor. If the charge is distributed evenly across the surface of the conductor, then this charge, every point on this conductor is causing an electric field strength radially outward of the conductor, and that electric field strength is equal at all points because the charge is distributed evenly across the conductor. Only because the charge is distributed evenly across the conductor can we say that, yeah. Which means that around the electric field strength E at any point that is equidistant from the core of the conductor is the same, right? So, and then of course, since this is an electrical conductor, you cannot have an electric field inside, because if you have an electric field inside and there's a voltage difference, that means current will flow. So there's, theoretically speaking, ideally speaking, this is a point conductor. So there's no voltage difference inside the conductor itself. So the electric field strength, we will ignore electric field strength inside. We only talk about electric field strength outside the conductor. Unlike the magnetic field derivation that we did, where we took inside the conductor and outside the conductor cases. So here we will only consider outside the conductor. So the E will be a constant at every radius away from the center. So we will be able to take it out of the integration. And the Q will be the charge distributed across the surface of the conductor. So we end up with, and of course the area that we were talking about is this area of the cylinder that has a length of 1 meter that is enclosing the conductor. So the area is this area of the circle multiplied by the length, the perimeter multiplied by the length. So it's 2 pi you know, if we're talking about x, so 2 pi x times the 1 meter. So ds is 2 pi x times 1 meter. So we take E out, and epsilon E times 2 pi x times 1 meter is equal to the charge enclosed.
I see.
Yes?
2 pi x times the length, that's a volume, it's not a surface.
No, it's a perimeter times the length. The perimeter is like the length. You know, take this sheet and open it up, right?
The faces.
No, I'm ignoring end effects. I'm assuming this conductor is, you know, pretty long, so 1 meter would be a reasonable enough length to ignore the effects of the ends. Yeah, I'm ignoring the ends of the. So I'm only looking at the area because again the electric field is emanating radially, right? There is no electric field emanating axially. That's the assumption. The assumption is that all the charge is distributed on the surface of the conductor only. Okay. So E times 2 pi epsilon E times 2 pi x times 1 is equal to the charge enclosed, assuming Q is the charge enclosed. I can rewrite that in terms of electric field strength, which is equal to Q over 2 pi x. And again, once I know the electric field at a certain distance x away, I would like to be able to look at the voltage difference between two radii around this, so this cylinder and another cylinder. I would like to look at the voltage difference between these two cylinders around the conductor. So to do that, I would have to integrate the electric field I would integrate the electric field based on the distance away from the conductor. So I would integrate it from a point D1 to D2 in space around the conductor. So points D1 and D2. This is the conductor. I have point D1 here, point D2 here. D1 here, point D2 here. And this is my distance x, so this is my dx, right? So I would have to integrate the electric field strength. So electric field is in volts per meter. I would like to calculate volts. So I would have to multiply this volts per meter by the distance, right? Volt per meter by the distance, so that I cancel that. What distance? It's the total distance between, you know, any 2 points in space around the conductor. I just chose D1 and D2. Okay? So you perform the integration between points D1 and D2, and you end up with the voltage between any 2 points around the conductor due to charge Q deposited on the conductor at 2 points D1 and D2 away from the conductor. Okay? So I calculated the voltage difference between these 2 points due to this conductor. How about if I add this conductor? This conductor is also emanating electric field, right? And I can calculate this electric field at a certain distance, you know, here, and at a certain distance, so here, and a certain distance here, right? Away from this conductor, right? This D1 and D2 were the distances from the center of the conductor. Distances of these 2 points on the circles, because again, this whole circle has the same electric field, right? This for this conductor, this circle here, the electric field strength here. This is a surface with the same electric field strength E1. We agree? And then this is another surface with another so it's an electrical field surface, if you want to call it, right? So all the electric field strength around this surface is the same, so E2, right? I would like to I calculate the voltage due to this conductor only. Now, this conductor is also within this space, within this vicinity of this other conductor. So it is affecting the electric field at these 2 points. Do we agree or not? Yes? No? Yes? No? How does it affect it? Assuming it carries charge Q2, how does it affect here? Come on, guys. What is this distance? D3, for example, and this is D4. This is carrying charge Q, and for simplicity, let's say this also carries charge Q. So, do you agree that this conductor with charge Q deposited on it will affect the electric field at points 1 and point 2? And if I want to calculate the voltage difference between points 1 and point 2 due to this specific conductor, I will use this equation, right? So Q over 2 pi epsilon, natural log D2 over D1 volts. This is the voltage between these 2 points due to this conductor. How about now I bring in another conductor into the picture? How is this other conductor going to affect? So this is V1, this is V2. So V1 is equal to Q over 2 pi epsilon natural log D2 over D1. How about V2? What is V2? V2 is the effect of this conductor on the voltage between these 2 points. What is that equal to?
Q over 2 pi epsilon.
Exactly. Q over 2 pi epsilon
DC over
natural log D4 over D3. We will integrate from the closer to the further away. Okay, just because this is closer to the point 2 is closer, I call this D3. So D4 over D3. So now what is the total voltage between points 1 and 2? What is V12 now? V1 plus V2. It's going to be V1 plus V2. It's the voltage due to this charge plus the voltage due to this charge at these 2 points. Because this voltage is actually, this V1 is the voltage between points 1 and 2 due to this charge. And then this voltage is the voltage between points 1 and 2 due to this charge on this conductor. Okay, so you will add them like we did for the inductances, guys. Exactly the same procedure here. Right, so we'll add this and this together, and then after you have the voltage between 2 points, you can find the capacitance between 2 points by dividing by the charge. If you're C equals Q over V. If you would like to find the capacitance between 2 points, and you want one way, of course, I would like to find the capacitance between what? 2 points, for example, or 2 conductors. Not 2 random points in space, right? So 2 conductors, and I will bring this point D1 to here. If I bring point D1 to the surface of this conductor, what is D1 equal to? The radius of this conductor, if it has a radius r. If I bring point 2, how about D2? D2 will be the distance between conductor 1 and conductor 2. Right? If I bring point 1 to the surface of the top conductor, right? Bring point 1 to the surface of this conductor. So D1 in this equation is equal to the radius. How about D2? Yeah, it's going to be the distance between conductors 1 and 2. So it's going to be D12, for example. I'll bring point 2 to this conductor. I want to find the capacitance between the 2 conductors. Right? So to find the capacitance between the 2 conductors, I have to, these 2 points in general in space, I have no use for that of them in space. I'm not going to find the capacitance between 2 points in space. I find the capacitance between 2 surfaces with different charges deposited across them. Right? So for me to find the capacitance between these 2 conductors, I would need to find the voltage difference between these 2 conductors. So take this point 1, bring it on the surface of this conductor. Take this point 2 and bring it on the surface of this conductor. Right? So D1 will be equal R. D2 will be the distance between the 2 conductors. How about here? D3 will be what? Remember, I brought point 2 to the surface of this conductor. So D3 is what? Is the radius as well of this conductor. And D4 is the distance between the 2 conductors. Okay? I don't know why is this confused. No, it's not okay. So there's an example in the next page. Maybe it will be clear to example on the slides. So generally we will be using this equation all the time, okay, for voltage between 2 points in space, right? We just have to figure out these 2 points. Where do you put them? You will put them on the conductors where you want to find the capacitance between them, voltage between them, so you can find the capacitance. Right now there are just two general points in space, D1 and D2. They are of no use to you here. We want to find the capacitance between the tower, conductors, and the ground. Right? We want to find the capacitance between this conductor and the tower and a point of zero potential. Right? So this conductor in the tower carries a current corresponding to a charge, and there's a ground potential here. These two have a charge difference between them, and they will have a voltage difference between them, and a corresponding capacitance between them. That's what we want to calculate. So first we started with a general case. I have a conductor and I have 2 points in space around it. I found the voltage difference between the 2 points. I really don't care for these 2 points in space. What I care for is bringing this point to the surface of the conductor and bringing this point where? To maybe the ground potential, a point of zero potential. So these are now the 2 points, my neutral point or my ground potential and my conductor.
What happens if you do the opposite? So you take the first point to the ground and the second.
Well, you can, doesn't matter. Yeah. Does not matter. It does not matter. We just started with the closer one. I mean, the way that they did the integration here, they integrated from D1 to D2, from the closest to the furthest away. So from the radius in this case to the distance that's far away. Right? You can do it that way, or you can do it another way. No, I would, because again you would use the equation in the textbook, right? I mean, I think it makes sense that way. I think if you do the opposite, then you will get a negative sign. Right? It's like measuring with a voltmeter. You measure in one way, you will get a positive voltage. You measure the other way, you will get a negative voltage. It's like, I mean, again, I think it's exactly the same. If you do the do the further away one and then the closer one, then you will get a negative sign. So they generalize. So the textbook generalized this V12 equation, the voltage between these 2 points in space, to this conductor. So here they are telling you that this equation says that the voltage between points K and I. Points K and I, they will bring them on conductors now, right? My interesting points are the voltages between the conductors. So the voltage between conductor K and I due to conductor M carrying charge Q on it. Okay, this is what this equation means, right? So VKIM is the voltage between points K and I in space, or now we brought these 2 points in space to the surface of conductor K and the surface of conductor I, due to the charge on conductor M. Okay, so it will be Q over 2 pi epsilon natural log DIM over DKM. So DKM is what? DKM, if DKM is the distance between conductor K and conductor M in space. Sometimes you will calculate DKM for the conductor itself. If M equals K, right, I end up with DKK. DKK is the radius of that specific conductor. If M does not equal K, it's the distance between one conductor and the next one. Okay, let's apply the equation in an example. I don't know why this is... You get it? You get it? Okay, so we will create a summation, right? We will create a summation where the voltage between conductors K and I is equal to 1 over 2 pi epsilon, the summation of charge on conductor M. So it's the voltage between two conductors due to any conductor in space. Any conductor in space. This conductor can be K and can be I. Or it can be, for the general case, M. And M goes from 1 to M. 1, 2, K, I, small m, capital M, right? All of the conductors. We want to find the voltage between conductor K and conductor I due to all the conductors in the vicinity of these two conductors. So we will just apply this summation. Yes? Okay, so take out a piece of paper and pencil and apply it for single phase. So here, I'll give you a... No, really, wake up and apply it. So this is conductor, two conductors for a single phase system. two conductors for a single phase system that have a distance d between them, and they have a radius r. I would like you to find, VAB. This is A, this is B. Find VAB. Please write it down. For half a bonus point. It's not worth it. No. Okay, maybe I will not curve the final exam and, No, please take out a piece of paper and pencil and apply the equation. Guys, it's just an application of the equation, really. And they both have, so this has, this has current I, so charge Q on top of it. So this has current, I in the opposite direction, so it has charge minus Q deposited on it. Right? So one has, the currents are in different directions. It's a single phase circuit. The current is going one direction in one conductor, other direction in another conductor, so the charge is opposite. One is Q, one is minus Q. So this is summation with two terms. Right? Just apply this. It's a summation with two terms. I have two conductors. I want to find the voltage between conductor A and B, or conductor 1 and 2, or conductor light and neutral, whatever you want to call it, right? It's easier for me when you're doing work. Huh? Yes.
What's the variable
M is conductors. Conductor 1, 2, 3. It's just a summation of the effect of all the conductors. So this is, M starts with 1, right? It means for the first conductor that has charge Q on it, blah, blah, blah. For the second conductor, M is equal to 2. For the second conductor that will have charge, in this case, minus Q on it.
And the I and K are two different points in space.
Two conductors in space. Because remember, initially we started with 2 points in space, right? I really don't care to find the voltage between 2 points in space. I want to find, like we did for the inductance. We started with 2 points in space. Then I did what? Then I brought 1 point to the surface of my conductor, right? And then 1 point in space at infinity. And we are able to simplify the equation. Yes.
Isn't that just the line-to-line voltage?
Yeah, it's the voltage between these two conductors. In a single phase circuit, this would be the line to neutral voltage. This is a single phase circuit. You have two conductors. It can be phase A, phase B. It can be phase A and neutral, right? It doesn't matter. I'm just giving you two conductors with different charges across them, and a certain distance between them, and they have certain radius. And I'm asking you to find the voltage between the two conductors, because this voltage will correspond to a certain capacitance. Apply the equation. Come on, you have to be able to apply the equation. What's one bonus point, not half.
What do we need to find?
VAB, where A is K and B is I. Come on, guys.
Do we know the charge of
Yeah. One is Q, one is minus Q, because it's a single phase circuit. Current goes in one direction, back in the other direction. Yes, sir.
How many charges are there?
One conductor is charged with charge Q, it's evenly distributed. And the other one is with minus Q, evenly distributed. This is a 1 bonus point quiz. 1% bonus on the whole grade. Yes.
Is the charge equal? Minus Q.
Yeah, equal but opposite signs. One is Q, one is minus Q. They're exactly equal. Remember, it's a single phase circuit. It makes sense that they're equal, right? So, current goes and comes back, same current comes back to the source. Write your name. And try to simplify the equation. Don't use Q1 and Q2. I gave you Q1 and Q2. Substitute them. Q1 is equal to Q. Q2 is equal to minus Q. Substitute and simplify. Yeah. Simplify. Can be simplified further. Like you use the logarithmic identities to simplify. It's correct, but just use the logarithmic identities to simplify. It's more fun to have quizzes in class, really. Next year I will change the policy. It gives me a break, right? So I can walk around.
I don't understand.
But what? Apply the equation. What's
Okay, it's fine. It gives me I don't understand.
K is conductor K. I have conductor A. I is conductor B.
So you only have one
I have what?
for M for the.
Why? M is 1 until all the conductors in the area.
You only have two.
Exactly. So you go from 1 and 2.
So when M is equal to, can I substitute it with B as it's the second?
Yeah, of course. First one is A, second one is B. You only have two conductors. Simplify. I gave you the radius of the conductors. Radius is R. They both have the same radius.
And Q is zero.
Q will be 0. Why?
Plus minus Q.
Now write it down. But before you imagine math, write it down. Yeah. Yeah, but why did you? Where happened to Q? Took Q out, right? We ended up with natural log something minus natural log something, right? Natural log something minus natural log something is 2 over each other. This is what Q outside, right? The one where you simplify epsilon, and you put the Q outside. Here? Here. Okay. You take the Q outside, you're left with the natural log over R, minus natural log. This is natural log of B over R over. Yeah, exactly. Simplify properly. So this has nothing to do with power, guys, but it has something to do with you guys writing. You're not writing enough. Your name. You have to write your name.
Yeah, but I just want to check if it's.
It's for sure not the final form, so you did not.
I can't cancel this with this.
The radius is the same. The two conductors have the same radius, and they have the same but opposite charge. So I don't want to see Q1 and Q2. I want to see Q and minus Q. I don't want to see dBA, dB, I want to see D and R. There's one D. D is distance between the two conductors. R is the radius of each of the conductors. Come on.
But R is not even in the equation, right? Which symbol represents R?
D.
D is the distance between them, right?
Okay. What is K? K is, for example, conductor A.
Yeah.
For example, if it's A, can you have a DKK or not? K is one of the conductors in space.
You can, when I'm equal.
When DKK, what is DKK?
DAA.
What is DKK?
DAA.
Is what? What is DAA?
Oh.
Yeah. Right? Remember, we're bringing one in the general equation. We're bringing one of the points to the surface of one conductor, the other point to the surface of the other conductor. Right? So the natural logs will always have the radius of one conductor, the radius of the other conductor in there, and they just both happen to be the same. I simplified it for you. Right? Generally, I can make it different.
What if it was DAB? It still would still be the same R, right?
DAB is the distance between them. Here I called it D for simplicity, so you don't have to deal with DAB and DBA. Yours is correct. You want to fix
That's
something?
correct.
I think so.
I feel there should be something fixed with the DAB. It should be D plus R, right?
No, forget about the. No. We're ignoring the. Okay.
That's one that,
Yeah. The distance between them is D. The distance between the two cores. Okay. Forget about the
plus R.
plus the R. The textbook even ignores it. We will assume the conductor is much smaller compared to the distance between the two conductors. Simplify.
I don't know how to simplify that.
What do you mean you don't want to simplify? This is math. Has nothing to do with power. Huh? What is this? What is this? How do you take the square between the two? It's a math class now, right? Natural law. Work of art. Okay, we have to continue, guys. Come on. Just write your name and what you have. And come on. Thank you. Design. We only have the summation only have two terms because we want the summation is from m equals 1, small m equals 1 to capital M. Small m is equal to 1 starts with 1. And then what's capital M with 2. So I only have two terms. Why do you have three terms, four terms in the summation? So the summation will have two terms. This is
and Q1 natural log blah 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 plus Q2 natural log blah, that's it. Right? So it only has two terms. No, Q1 is Q. Q2 is minus Q. Right? That's it's okay, just write your name. It's a bonus. It's not huh? So she needs more time. You're supposed to be in your time. Inshallah, if you can. Yeah. Well, if she gets one point, I'll give you. Okay.
This was lots of fun. Next year, for sure, I know what I'm going to do. Okay, so again, we want to apply this summation. We apply this summation. This summation will have two terms because capital M is equal to two conductors, conductor A and conductor B in the case of a single-phase circuit. So for the case of a single-phase circuit, we go. The solution is here actually on the next slide. So for those that had the slides, for those that had the slides handy, the solution was there. So again, it was two terms to the summation. Q natural log two distances. The bottom distance again, it's for this is the effect of the first conductor on itself. So first is x, this is x. So dxx. Dxx is the radius of the conductor x. And then this is dxy. Remember the summation is here. Vki summation 1 over 2 pi epsilon naught qm natural log dk. So this is always the first of this is AB, then this is always A. A1, A2, A3, A4. In our case, it was AB, right? For the second term, AA for the first term. So it's if K is A, then this was A, and then A for the first term. So the denominator was DAA, which is the radius. The denominator of the second term was DAB, which was the distance between the two conductors, right? So this is DXY, this is DXX. So it was just a direct substitution, right? Direct substitution and then simplification based on natural log properties. Yeah. So here they started off with all the distances and radii being general, different, and then simplified. So they said that dxy is dyx, the distance between the conductors is equal to d, and that dxx and dyyy are the radii of the conductors, and they're equal to r. The same thing we assumed in our solution. So Vxy, which is the voltage between the two conductors, was what you calculated. So this is Rx and Ry are the same, so it goes out as natural log d over r. Okay. So any questions? So now we have the voltage. So if we have the voltage between two conductors, if I would like to calculate the capacitance between the two conductors, I do what? For 1 meter length, the capacity between the conductors is then the charge on the conductor divided by the voltage. That's really it here, right? It's the charge divided by the voltage. So it's pi epsilon. It's again they should have simplified it here, but again it's they
They should have put Q.
huh?
They should have had the Q above and Q.
Yeah, no, but they cancel. Q over Q over pi epsilon. The pi epsilon goes to the top, to the numerator, and you're left at the natural log in the bottom. And then they they simplify that here further to both r's are the same, so you end up with a natural log d over r. So if rx equals ry, then cxy is equal q over vxy. So okay, everybody's okay with this, calculating the capacitance between the two conductors? How about if I want to calculate the capacitance between one conductor and neutral?
There's no radius for neutral.
Hmm?
There's no radius for neutral.
No, but
Or
apply the equation. Apply the equation. So the charge in there will be 0, right? So you will have half the voltage. You will, if you apply the equation, apply this equation, and the charge will be 0. One conductor is what? One conductor is one conductor phase A. Other conductor will be, instead of phase B with charge minus Q on it, will be 0. So remember you had the d squared over r squared, and the squared caused this 2 to vanish, right? So now there's no squared anymore because this term is 0. If this term is 0, then there's no squared, so this 2 will not vanish. So what will happen to the voltage? It will be the same. It's 1 over 2 pi epsilon times q natural log dyyy over dxx, right? So and dxx is the radius and dxy is the distance. So it's exactly the same as for the voltage between two conductors, but divided by 2, right? The 2 does not cancel because we don't have this second term, right? That's the only difference here. So that's Vxn is equals Vyn is equal to Vxy over 2. Does everybody see where this 2 came from? Right? It's just that the square that we had before does not exist because the second term of the summation becomes 0 because you're looking at the conductor and ground. Okay? Or something, or another conductor with no charge on it. Right? With Q equals 0. Same equation. So if the voltage is divided by 2, what happens to the capacitance? Look at the capacitance. If the voltage is divided by 2, the capacitance is multiplied by 2, right? So it's Vxy divided by 2, so you multiply the capacitance by 2. So the capacitance line to neutral is 2 times the capacitance line to line, right? So it's much more dominant actually than the capacitance between two conductors. It's 2 times that. And of course I forgot a 2 here. There's a typo here, right? So it's 2 times this. It's 2 times pi epsilon over natural log d over. It's written properly at the last slide, on the last slide. Yeah. So any questions on this? For 3-phase, we have time to do another quiz? We have time to do another quiz. I'm not going to start something else anyway. So for 3-phase, guys, another short quiz. For 3-phase, here, come on, I'm serious. Another piece of paper. Another piece. It's a lot of fun, really. It's for me. It's assume that the distance between the conductors is d, and the radius of the conductors is r. The radius is r, and then this is phase A, QA, QB, QC. What do I know about 3-phase systems? I know that IA plus IB plus IC is equal to 0. Same thing. QA plus QB plus QC is equal to 0. That means so QA plus QB plus QC is equal to 0, right? That also means that QC is equal to minus QA plus QB. This will help you solve it. So I would like you to find the voltage, then the capacitance. Voltage. Yeah. Find the voltage. Yes. Between two. Find the voltage VAB. This is A, this is B. Find the voltage VAB between conductors A and B. Yeah. You're not referring to the yes. Why will it have 6 elements? Remember, the summation is on all the conductors. The effect of conductor 1, conductor 2, conductor 3. So the summation will have 3 elements here. Why 6?
I mean, there's going to be A, B,
3
and
conductor A, B, and C. So this is conductor 1, then conductor 2, then conductor 3. There are only 3 conductors in space. Why 6? Just write the summation and use this identity and simplify it just a little one-step simplification. You don't have to go all the way to the end here. Just write the summation, write out the full summation, and then simplify using the identity that I gave you. And that's it, stop there. So this will be another half percent more. First one is 1%. Ah, come on. 1.5%. Too much. I mean, more than 1.5%. Too much. Write them. Please don't ask right. Write the summation. Yeah, it's effective QA plus effective QB plus effective QC. Yeah. Yes, QM is going to be QA, then it's going to be QB, then it's going to be QC. And that's it. Simplify using the identity I gave you, the identity that the charges sum to 0. So simplify one step, do one step simplification. Don't need to. That's it. They're taking a quiz. Yeah, she's I know. For bonus, and not I'm asking them to calculate the voltage between two conductors. Yeah. Okay, so we have to stop. Come on. We have to. I have to finish the capacity. So stop. Calculate the voltage between the two conductors. Yes, you're right.
I don't see that.
Almost. Huh? Write your name. That's it. No, this is half.
You have to simplify.
No, it's simplify. So simplify one step using this. But there's no time.
So you have to quote it for attendance.
Quote it for attendance.
And then
You have it.
it's here, there are really good.
No, actually, then one equals 0. It was a bonus quiz, right? I want to test in the class. Yes. Yeah, exactly. Yeah, you're right. Okay, so let's wrap up the voltage. So we did the single phase, and for three phase, guys, it's again the summation has three terms. So one point here that to note is this last term is distance between AC and distance between BC. Does this include radius? No. So this is, and these distances are the same. So this last term will go away. It's 0. So you'll end up with QA over QA plus QB natural log D over R or something like that. So same substitution we did before. So you will end up with VAB equal to 1 over 2 pi epsilon QA natural log D over R plus QB natural log R over D, and you can simplify that a little bit. Yeah. No, you cannot, I guess. So, and then similarly, you can do the VAC, you can calculate VAC as well from using the same equation, right? So any questions about the calculation of voltage? No? If I have voltage, of course, I can, if I have VAB, I can shift it by, multiply by square root of 3 and shift it by 30 degrees to calculate, or, VAN. You calculate the line voltage. If you want the phase voltage, you can use the identity between the phase voltage and line voltage that we did before. Or you can, again, you would have to, or you can calculate the voltage. In that case, you would have a third conductor in space with charge 0 on it, so that you will consider that. You can rewrite, you can write the equation down. If you would like to calculate the voltage between the line and neutral, you can do the same thing we did before by considering a third conductor in space, or after you calculate the line voltages, you can divide by square root of 3 and shift by 30 to find the phase voltage, and vice versa. Right? Or if you calculated the two line voltages, you can add the two line voltages, and the two line voltages will be equal to 3 times the phase voltage. So whichever way you calculate the phase voltage, at the end we're always concerned about calculating the phase voltage, right? Because we want to calculate the voltage between the capacitance between the conductor and the ground, right? So you're always going to start with calculating the line voltages, and then from there you would calculate the phase voltage. In three-phase, you would calculate the phase voltage by summing up the line voltages and dividing by 3. And what you did in the quiz was just calculating the line voltage. So you sum up the two line voltages and divide by 3, that will be your corresponding phase voltage. At the end, remember, you're going to be applying these equations. This equation that you had here is the core. This equation is the core. I can give you any configuration, and you can calculate the capacitance between lines. If in the three-phase configuration, if the D was not equal, you would have not ended up with this simplified equation that we had here. So this is the voltage between two conductors, and I can calculate the line corresponding phase voltage. From calculating two line voltages, I can calculate the corresponding phase voltage. You end up with this simple equation, right? This simple equation, 1 over 2 pi epsilon QA over natural log D over R. This is the phase voltage between, this is the voltage between conductor A and the ground, right? If the distances were not equal, like the inductance case, you will not get equal capacitances per phase. The way we solve that is by transposing the lines. We talked about this transposing the lines before, like in the last class. So again, of course, from after you calculate the phase voltage, you can calculate the phase capacitance by QA over VAN. Right? We did that for the single phase. I will not do it again for the three-phase. And then this slide talks about transposing the lines. If the lines are properly transposed, then VAB is equal to VAC shifted by 30 degrees, shifted by 120 degrees, is equal to VCA or VAB. All the three line voltages are equal, which means all the three-phase voltages are equal in magnitude, but they are shifted by 120 degrees apart. That is only when the lines are fully transposed, right? Because in the triangular configuration I gave you, the distances were equal, and the derivation for the capacitance was assuming that these distances are equal. If the lines are in this configuration, these two distances are equal, but this is not. If this is not, then you cannot use this value for capacitance anymore, right? So if you cannot use this value for capacitance anymore, then the value for the phase A capacitance, phase B capacitance, phase C capacitance are not the same, which means you don't have a balanced system, which is not the case. We will transpose the line so that we have a balanced system. So where do you calculate this D that you use, that I used before? You calculate the D that we used before from this equation. So this is D12, the distance between conductor 1 and 2. D13 between 1 and 3, 2,3 is between conductors 2 and 3. The cube root of these distances will give you the 1D that's equivalent D, the geometric mean distance between the conductors. So, and then you just use the same D in the equation that I gave you. In the equation that you applied now, it's the same D. But where does it come from? It comes from this equation. Yes?
But all the small d's are the same. The geometric mean distance is in the middle of the
No,
conductor.
if they're all the same, then it's D cubed. Cube root of D cubed is D. Right? So it's what we had before. It's the same, D. If they're not the same, then use the actual distances, take the cube root, and use that 1D in the equation that we just applied. Right? So this is the summary of this chapter. we calculated the resistance, we calculated inductance here, and we calculated the phase to neutral capacitance of one of the phases, right? So this chapter is over. I will give you some homework. It was a lot of fun doing the quizzes. Honestly, it's very, very relaxing for me, huh?
Wait, how many quizzes?
We did 2 quizzes today to compensate for not doing quizzes before. Really, it wasn't intentional. It was, like I didn't find people paying attention, so I was like, okay, let's do 2. It was more fun, like than explaining the material.